Hello everyone, this is Sadia. I'm a master's student in UBC Okanagan campus. Today I'm going to present my recent study on modeling the effects of transit preferential treatments on the Transit Reliability Index. We all know that public transportation is a sustainable alternative travel mode since it reduces traffic congestion, parking demand, collisions, and vehicular emissions. Transit agencies are adopting several transit preferential treatments to minimize transit delay and improve its level of service. However, it has become challenging to efficiently operate transit in mixed traffic conditions. Hence, it is critical to properly plan the alternative preferential treatments and test their effectiveness in different traffic conditions. There are several measures to test effectiveness of the preferential treatments. For example, delay and travel time. Among them, the reliability is a crucial factor. This reliability often refers to the variation of travel time. Since transit arriving late or early have significant negative impact on the passengers. Census have shown that transit operating in congested mixed traffic scenario generally encounter greater variation in travel time. Hence, this study investigates the effects of most common transit preferential treatments based on reliability, that is, variation of travel time. Here in this study, reliability is defined as the deviation between the runtime and scheduled time in a given segment of the corridor. For this, the study area is for the study area, a busy congested corridor is chosen, which runs through the city center in Kelowna, British Columbia, Canada. Namely, the corridor is a Springfield Road, and the intersections are namely Gordon to Zipprick intersection. The length of the corridor is close to 5 kilometers. This is a two-way arterial, 2 traffic lanes on each side. There are 8 vehicle-actuated signalized intersections, 2 bidirectional transit routes, number 8 eastbound and westbound, and number 11 eastbound and westbound, and there are 28 bus stops. The network was coded using the Vising platform version 11. The network coding involves the lane configuration, road grid, vehicle-actuated traffic signal timing, reduced speed areas, pedestrian crossing, transit routes, bus stop location, including the stop skipping probability at each stop for the transits, and passenger boarding and alighting. All of the data were collected from the local government, City of Kelowna, and BC Transit. The model is developed for 3 peak period: PM peak period 3 to 5 p.m., AM peak period 8 to 10, and midday 11 to 1 p.m. For each case, average results of 50 simulation runs with different random seeds are extracted. Here shows the calibration result of the model. The model is calibrated using the traffic volume, and GEH value less than 5 was achieved for every cases. And the model is visually inspected and run. Every model was run over more than 100 times by differing the random seeds and with modified driving behavior parameters, which is Weidman 74. The average standstill distance 2.1, additive part of safety distance is 2 meter, and the multiple part of safety distance is 1.8 meter. After that, the models were also validated using real data collected from the field. The model was validated with by Q-length and travel time of both car and transit. For Q-length validation, for example, we have chosen an intersection with 4 approaches. Here, the values represent the simulated minus the field or observed divided by the observed. We can see we have The error is close to 6 to 17%, which is reasonable. 4 scenarios were developed in the model. They are transit signal priority, queue-jump lane, exclusive transit lane, and a combination of transit signal parity and queue-jump lane. Based on the travel time and delay results and visual inspection of the existing scenario, the new improvement scenarios were planned. For example, transit signal priority was planned for the PM peak at the following intersection approaches, which are Cooper southbound approach, Bird southbound and westbound approach, Gordon westbound approach. The reason behind this is we exhibit significant delay in these approaches, and others were also planned accordingly. Here, the transit lane was planned from the Cooper intersection to the Birch westbound direction, since travel time for transit was greater for this direction and up for this segment. After that, a random parameter regression model has been run. In order to capture the reliability or run or on-time performance of transit, model runtime and schedule runtime have been recorded in every segment between 2 consecutive bus stops in a given route. From that, deviation between model runtime and schedule runtime has been recorded to address the on-time performance of transit. So here, reliability refers to the deviation of runtime between model and scheduled in a 2 consecutive bus stop segment. Here the table shows the results of random parameter regression model. A positive relationship reveals a higher deviation which refers to a lower reliability, whereas negative relationship means deviation decreases with the corresponding scenario. The model results suggest that the variation is higher along the westbound corridor. All the remaining alternative transit preferential treatments showed negative relationship, indicating an increase in reliability. However, except TSP plus QGL over the day and QGL during AM alternatives, all other treatments show heterogeneity by showing a higher standard deviation than the mean. With no heterogeneity, TSP plus QGL shows a significant negative relationship. This implies that TSP plus QGL might cause consistent improvement in reliability over the day. Another 2 important fact is the result of the random parameter regression model suggests that alternative scenarios can affect deviation both positively and negatively, and improvement techniques should be adjusted in a given scenario during a definite peak period. Thank you for your attention to my presentation.
Hello, everyone. Hope you're having a good day. My name is Mohammed Al-Agrudi, as he just described. So I'm going to be sharing with you some of the research I did on my thesis work over this past year. So, oh, sorry. There we go. So I'm going to start off with a little background. I'm going to try to run through this, basically, what is mobility as a service? So mobility as a service seeks to unify transportation and information resources to streamline trip making for the individual user and consolidate demand for multiple operators. What this means is basically you get a one-stop shop for the user and for the operator. So if someone wants to go and see what options they have for getting from point A to point B, they have one app where they can do that. Very convenient. They can choose their comfort level, they can choose their pricing level, and similarly the transport operators have that one-stop shop where they can have users come to them. WIM is an example of a really comprehensive citywide mobility as a service system in Helsinki, Finland. So why did I look at mass? So I graduated from Montreal, and when I got there, all I had was my phone. But even with my phone, I still had many options. I had options for bike share, had options for ride share, had options for metro, bus, and of course Google Maps could tell me where I needed to walk, and it was really easy to get around that way. But when I came for my master's degree, it's a really different story. It's mainly just cars, just roads and cars. I did bike around for a year, and it was very dangerous, really life-threatening stuff. But eventually, I did get a car, and I got to enjoy sitting in traffic with everyone else. So there's a lot of externalities associated with car dependency. It's bad for our health for many reasons. There's lots of costs involved, lots of time lost, and it is one of the largest contributors to greenhouse gas emissions. Mobility as a service can solve some of these issues. For example, services are affordable. You can choose what kind of service you're looking for. Do you want to bike somewhere, or do you just want to walk half the trip and then take a bus? Which one's cheaper for you? Which one's more comfortable? Multi-leg trips promote health. There's convenience because everything is at the phone app, and convenience of choice. More sustainable, less externalities. Here are some key definitions. So multimodal just means variety of transportation modes: walking, cycling, personal vehicle use, ride hailing, public transit. Integration, it's the connection between these different modes, how we're going to move from one mode to another in a mobility as a service system. Performance factors, these are how I will be measuring the effectiveness in transportation engineering terms, such as throughput, delay, travel terms, and lots of sustainability factors. We have many measures of economic, environmental, and social impacts. For this presentation, I'm going to be mainly focusing on the performance factors, since that is the was my main focus in using Visum. So here's another list of key concepts for mass. It needs to be focused around the user. It needs to be convenient, affordable, sustainable, multimodal. Information services are a big part in offering good mobility as a service systems, payment processing, and in a real world mass situation, there would have to be a lot of public and private partnership. So problem statement. Studies to date have not explored the hard performance measures of modally diverse networks in depth. There's still a lack of understanding as to how these various modes interact with each other and how they impact traffic performance. So I posited 3 research questions to try and achieve this objective. 1, how is performance affected on a microscopic basis? So these are effects that can be observed by the individual as one person going through the network. 2, how is it affected on a network-wide basis? How does this affect the network as a whole? And 3, how do these modes interact in terms of performance effects? So that comes more into statistical modeling. To answer these questions, I came up with some experiments. So first of all, I'll go through our site selection. So here's the regional network in Orlando. Points of interest, the first one is iDrive. This is a study corridor. It is a mixed use area. There's lots of restaurants, lots of hotels. This is mainly for tourists. People can go there to shop, eat, do whatever they want to have fun, just a general leisure area. The airport's right there. We have our theme parks a bit to the west. The central business district is also quite nearby, and UCF's up in that corner just for fun. So here is a little map of our network and the intersections we're looking at. As I described, there are multiple modes available. It is a tourist hotspot. We have many mixed land uses and a variety of traffic conditions, which made me think it would be ideal for analyzing a multimodal mass network. Data collection resources. Here's just a list of where I got all my information from. A lot of it was taken from previous consultant studies and publicly available traffic information, and some of it was taken from field visits, for instance, like travel times, flow rates, etc. The modeling stages went as such, starting off with data collection, going into geometry, going into signalization, vehicle compositions, vehicle inputs, driver behavior, transit inputs, pedestrian geometry, pedestrian signalization, and finally calibration. So I didn't want to go too in depth onto the calibration process, but basically was calibrated based on flow rates, queues, travel times, and general observations to make sure that these matched up with real life. So this was typically done by calibrating them to within a certain percentage of the real life observed values, and also through the Geoffrey E. Haver statistic, the GEH statistic as mentioned in the previous presentation. So I'm going to go through my modal variables and how I selected these levels. So first of all, demand. Demand just represented the overall flow rate through all modes through the network. So this was just basically a combination of all the data, and it included demand and persons per hours for all modes, because when we want to compare performance effects, we need to compare an apples to apples. So I can't compare cars to buses. I have to compare persons to persons, and this involved using occupancies, uh, which I received from the Lynx website, boarding and lighting data from the Lynx website. I took some data from some national studies for occupancies in regular vehicles, and of course, on a bike or on foot, one person is one person, so that was pretty easy. Transit. So the transit level one was decided on the existing transit, and the existing transit was at 20 buses per hour. Transit level two, upped I upped the buses per hour. I upped the frequency and I increased the boarding. Transit level three, I further increased the frequency and boarding. Rideshare. So rideshare, in the beginning, there's not really much data to collect on rideshare or taxis. So that had to be assumed to be captured in the calibrated model. So the level one for rideshare comes in at 0. The other levels were selected sort of arbitrarily based on a sensitivity analysis to see what gave me an effect when I input it into the network. And as such, I put the actual values here. Walking and the existing network, we have 1375 persons per hour walking through the network. Walking, and this includes at intersections, mid-block crossings, along sidewalks, etc. And walking level 2 is about 1.5 times walking level 1, and walking level 3 is 2 times walking level 1. And finally, micromobility. Again, there wasn't really much existing data there. When I was observing this in the field, I didn't observe any cyclists at all. I observed 2 cyclists at over 6 hours of observations. So I began it off at 0 persons per hour and just scaled it up to 1,000 persons per hour arbitrarily. So for design of experiment, I came up with 3 scenario tables, kind of progressively investigating what we had going for us. So the first scenario design was a definitive screening design. This is a very useful design when you have a lot of different variables. So when I'm trying to do an experiment on 5 different variables, I have to narrow down the experimental design as much as possible just to find which variables I really need to investigate. Once I found out those variables, it turned out that rideshare and transit were the most interesting variables for me to look at closer. So I performed the response surface design, which allowed me to capture quadratic effects on 2 variables within a limited design space, only 10 scenarios. And to finish it off, after that, I created a full factorial design on demand and transit. Oh yeah, by the way, so D stands for demand, R stands for rideshare, T stands for transit, W stands for walking, and M stands for micromobility. And as you can see, I just have the levels set up there. And in my final one, it was just a full factorial design with 6 levels each for demand and transit. So here's a better visual representation of the design of experiment. So at the maximum demand level, we have at capacity. As you can see, none of the experiments exceed this level, but we do have a little bit in between and a little bit at the existing demand level. Also, we have like you can see the splits between walking and transit. So scenario 1, this is just like a realistic existing scenario. But once we start throwing in ride sourcing and micromobility, we start seeing some interesting effects. So findings. So first research question was, how is performance affected on a microscopic basis? So here are the response variables I was looking at. We have vehicular travel times, sidewalk travel times, and queuing at bus stops. So vehicular travel time, statistical modeling. So the modeling process started off with data extraction from VSIM from the calibrated model, organized into data table, filtering of outliers via standard deviations, residual plots, and studentized residual distributions, stepwise regression and AICC comparisons to choose which models fit the best. And I tried a couple alternative model types, linear regression, generalized linear, data transformed regressions, And finally, I picked the final model selection using statistical diagnostics such as ANOVA, lack of fit, and coefficient t-testing. So here we have our first model for vehicular travel time, and what we found from the model was what was to be expected. So for vehicular demand, if you look on the left over here, as you can see, you see the classic quadratic relationship. As vehicular demand increases, our travel time also increases in a quadratic relationship. What was interesting, however, were the interactions. So as you can see here, we have a VD star TD interaction and a VD RD interaction. What this means is best explained through this figure right here. As you can see, as our demand level increases, as we increase the total demand to congestion, the effect of transit moves from being a positive linear effect to an almost flat effect. And similarly, rideshare shows the opposite behavior, where as we increase our demand to congested conditions, rideshare shows even worsening, a stronger linear effect. So just to summarize it up, um, the model shows a significant DT interaction, which suggests that transit does not increase travel time in congested conditions, as in adding more buses to conditions which are already congested has a very minor effect on travel time. Two, this interaction suggests that transit's potential as a solution to congestion. So if we go into the literature on this, this is a very popular point where we want to organize transit along already congested corridors which already see a lot of demand. This increases the exposure and the opportunity for transit to reach as many people as possible. And this also supports the side of the literature demonstrating a negative effect of rideshare, which gets even worse the more congested the conditions are. Next, we have average sidewalk travel time. As you can see, there's two modes that appear to affect the travel time. Obviously, it's going to be walking and micromobility. Increasing micromobility levels has a pretty big reduction in sidewalk travel time because, of course, more people are using those bikes. They're being able to get from point A to point B faster. But when we're increasing walking level, this causes a bit of sidewalk congestion, and we see an average 100-second increase. We also tested this out with a statistical model, and we also saw that through the statistical model that higher levels of micromobility do reduce the average travel time, but it also increases the effect of that walking variable. So what this translated to plain English, this means that micromobility reduces the travel time and walking slightly increase higher levels of walking slightly increases it. Notably, the WM interaction suggests that higher micromobility volumes adds to walking delay. This is likely due to conflicts between pedestrians and cyclists. And the way I modeled my network, I made it such that pedestrians and cyclists were able to share the sidewalk and were able to conflict and interact with each other as they would in real life. Legally, people have to use the bike lane, but in reality, people are often biking on the sidewalks. If you go to Orlando downtown, no one is riding their cycle on the streets. These results highlight the benefit of adding micromobility options, as well as the need for consideration to reduce pedestrian cyclist conflicts, wheels from heel separations, pavement widenings, etc. Queuing at transit stops. So rideshare was the only variable to have any noticeably immediate impact. We've seen an average 86% increase in travel stops between the low and high levels. From glancing at the data, there's no obvious relationship with transit. There doesn't seem to be a D or T relationship, directional queue. I looked at this from a lot of angles, but there was one factor which really did seem to affect it, which was the presence of a lay-by. So while rideshare caused slight increases in queuing, as shown in the first figure, we see here that with a lay-by, we enjoy almost 13 times fewer transit stops than without a lay-by. So this is kind of what I observed in the model. We had and stops with laybys, traffic was able to flow through without any conflicts. But especially at pickup points and drop-off points for rideshares, this was causing lots of backups, and similarly for transit, and this was causing huge delays for the network. So I did model it out and provide the parameter estimates right here. And our second research question, how does this affect on a network-wide basis? So Transit seems to reduce the network-wide delay by just about 6 seconds, and rideshare seems to increase it, which kind of corresponds to the results we found on travel time and queuing. In the final selected delay model, we found that all the modes had effects, and we also saw a quadratic relationship described here for demand and a quadratic relationship for walking. The walking quadratic relationship sort of indicates that after a certain threshold, the delay begins increasing when you add in more pedestrians. So, and similarly, speed shows the same results as delay, but just inversely. And remember, this is a network-wide model, so this considers all this considers the average for all persons' vehicles on the network. So, delay increases with demand, as expected, and the effect of rideshare is stronger than the effect of overall demand. So this tells us that rideshare is the worst mode of transportation for us in terms of delay. Transit and micromobility both show linear effects to reducing delay and increasing speed. Walking displays an interesting effect. Increasing walking level is beneficial up to level 2. Increasing it beyond level 2 results in worse performance. This implies that a threshold exists at which the delay from conflicts due to additional pedestrians outweighs the delay savings from removing one vehicle. And finally, we're going to look at the total queuing in the network. And it reflected what we saw at transit stops, is that rideshare is shown to have a pretty big negative effect on total queuing. Transit similarly shows a slight decreasing effect. As you can see here, each so each here, this represents a transit levels T1, T2, T3, and each color represents the rideshare level. So as we increase the rideshare level, we get a jump in queuing. But as we increase the transit level, we get a reduction in queuing. And this is because, of course, more people are using transit and less people are using cars. So finally, it's found that rideshare has the largest effect on increasing queuing stops. Transit greatly reduces total queuing, but does not have a significant effect at transit stops. Laybys are found to have the strongest effect at transit stops, and these results highlight the importance of infrastructure required to accommodate transit and rideshare. Stops with laybys tend to enjoy great performance and sustainability benefits. So I'm just going to try to conclude this really quickly. Transit performs the best out of all modes in terms of throughput and roadway impacts. Rideshare has the strongest negative effect across all microscopic and network-wide conditions. Walking has the potential to have minor adverse effects at high levels as pedestrian conflicts increase. Micromobility is the most attractive solution to non-vehicular travel, but again can cause pedestrian conflicts if not implemented right with separation. And finally, costs. Quality transit projects do have significant total costs. Costs over time and per mile are extremely cost effective compared to lane build scenarios. So I'm just going to finish this off with implications and future directions. Transportation design has recently been two-tunneled on prioritizing vehicles, but the bottom line has always been moving people. The research demonstrated major insights towards more cost and performance efficient movement of people in terms of modal focus, design considerations, and return on investment. The shift towards multimodalism cannot happen if lanes are being constantly expanded. We really need to focus more on designing around other modes, like with the laybys. We need to focus on preventing conflicts between pedestrians and cyclists, etc. Networks need to be transit-oriented along congested corridors. This supports both the literature review and the performance results shown in this research. So I'm just going to finish it off and say thank you for coming. There's a couple more notes I wanted to expand on. There's lots of funding challenges for transit in Orlando. Also, all these results are very specific to the corridor that was being analyzed. And there are a lot of hidden costs, which I didn't go into in detail here. But that is the end of my presentation, and I'm sorry I went a little over time, but thanks for attending.
I'm Zora Tatvijevich, graduate research assistant at University of Wyoming, and today I plan to present conditional transit signal priority for connected transit vehicles. So connected vehicles is a relatively new technology and still in deployment phase. Even though this technology has a great potential to improve safety, operations, and mobility, number of field tests is very limited, so we need reliable simulation models with these technologies. CV technologies enable safe communication between vehicles to vehicles, vehicle to infrastructure, or vehicle to device, or vice versa. And currently, US DOT has several ongoing programs with the aim to develop different CV-based applications. More than 50 applications based on the vehicle to infrastructure communication are already available to reduce crashes, decrease travel times, reduce emissions and fuel consumptions. Our research is focused on four applications. It's intelligent traffic signal systems, queue warning, dynamic speed harmonization, and signal control priority. This particular study is focused on signal control priority, and it's usually known as a transit signal priority. And it is a tool that makes transit system more reliable using an operational strategy to add the movement of in-transit vehicles or freight vehicles through signalized intersections. It can be implemented as a passive, active, and adaptive. Passive priority is based on already saved data of transit routes and ridership patterns, and it does not require any kind of detection. From another side, the active and adaptive priority depends on detection and information that are exchanged between transit vehicles and traffic controllers. Once when is TSP or signal control priority granted, there can be applied different strategies like green extension, earlier green, and in some cases phase rotation. Functionality of this application directly depends on the communication between transit vehicles and traffic controllers. So far, this communication was achieved through traditional detectors or later through a global position system. Even though these systems ensure call of TSP, they show some kind of imperfections, which can be solved with CV technology because it can ensure transmission of accurate and very detailed information 10 times per each second. So signal control priority in CV environment needs to have three components. That is a route unit installed on traffic controller to be able to receive and broadcast messages. Onboard equipment installed on the vehicles so these vehicles are able to communicate with each other and with traffic controller. And information exchanged between these two, it's usually known as a basic safety message. The content of basic safety message can differ for various applications, but in case of signal control priority, the vehicle sends a signal request message while the controller answers with a signal status message. And the same approach can be applied on freight vehicles, so it's known as a freight signal priority, or in another solutions for the transit like BRT. The test case of this study is the multimodal corridor of 10 signalized intersections in Salt Lake City, Utah. The testing was performed for afternoon peak hour from 4 to 6 p.m. And it's very important to mention that this corridor is served by major bus route. It's a route 200, and the future plans from the city include BRT, central running BRT for this corridor. The entire modeling as well as output evaluation were performed through Vissim microsimulation coupled with ASC3 software in the loop controllers. The communication among vehicles and infrastructure, which includes sending a basic safety message to routes and units, was coded using a Python programming language and embedded in a microsimulation, while signal control operations priority and controller logics were programmed directly in the controllers. Here is some important settings that we done before we finish our models. So it's important to change user-defined attributes that allows the model to convert VISIM coordinates into world coordinates. And it means that a vehicle with onboard equipment sends actual latitude and longitude coordinates directly to the controller. Another setting is related to external controller. Signal control priority logics is programmed directly in the controller. Since we had 10 intersections, for each of them was necessary to do settings. And what is interesting that the same settings that is done in simulation can be performed on a field. And basic safety message exchange between onboard equipment and the roadside units is coded in Python programming language that is supported by functions from VISIMS.com. In order to perform communication as a first step, it is necessary to define the detection range and what type of the vehicles is eligible to transmit the information. So in the example on the slide, we have vehicles that are out of the detection range and vehicles in detection range, what is designated with different colors. For example, these green are in range, these yellow are out of the range. So CV technology give us flexibility to use any kind of vehicle attributes, such as speed, vehicle type, coordinates, or traffic condition to define a detection range, what is completely different than earlier with the traditional detectors. Basic safety message contains as well position of the vehicle besides other information. Distance is computed using a harvesting formula. So the controller is updated with the vehicle position at each time step. Based on distance computation and the actual speed of the vehicle, the script was able to calculate exact arrival time of vehicle in each time step, what is transmitted to roadside unit. We applied two algorithms in our models. First algorithm is for the regular buses in a CV environment. And the algorithm applied only for the CV equipped buses. And it checks distance between a vehicle and the controller, estimated arrival time of the vehicle to the intersections, and the traffic conditions, actually queue conditions in front of the vehicle. Actually, COM functions give us options to make choice about criteria that we want to include in our algorithm. Another algorithm that is applied for the BRT, for the future running BRT, checks three different criteria and decides whether a bus needs TSP, and if yes, which level of the priority. Inputs for the algorithm are the time that the bus needs to reach an intersection, the number of passengers on board the bus, whether the bus is behind the schedule or not. The threshold for bus occupancy was 20% of the vehicle occupancy, what is I think 22 passengers on the board. The lateness is computed according to dwell times in both directions and the free flow speed of the transit vehicles. The roadside unit receives a basic safety message, and if it is any of the conditions fulfilled, the controller will receive the transit signal priority request. The location from which a bus requests TSP depends on the speed and distance from the intersections. When a bus leaves the intersection, the priority request is terminated. Since that we have different level of priority, we have different strategies that are applied. So if it's no priority, there is no any strategy that is applied. If it's low priority, there will be applied green extensions and earlier green. And in case of high priority, it will be additionally aid with phase rotation. Here we have a small video where we can see a vehicle which is out of the range, that will be pink, and a couple seconds later it will change in blue color. It means that it's entering in the range of detection. And on this controller app, we can see that it's granted transit signal priority. So it means that it fulfilled all conditions that algorithm proposed. Implementation of CV technologies in the TSP strategies would reduce delays. In our study, it showed that it's up to 33%, and it as well increased speed of the CV equipped vehicles, and it's up to 11%. As it is expected, TSP has some negative effects on the vehicle of the traffic from the side streets. In this case, it is up to 7%, but it is still less than for conventional transit signal priority. So some brief conclusion. The information from CV equipped vehicles can be used to create different forms of conditional priority. Basic safety message used in algorithms contain current queue conditions, vehicle speed, the distance between transit vehicles and intersections, the number of passengers on the board, expected arrival time of the vehicle, and schedule adherence. The algorithm is capable to introduce different levels of TSP while considering several criteria to grant the priority. Green extensions, early green, and phase rotations were strategies that are implemented in our models and for different combination. And generally, from 6 models, 6 scenarios that we had, models where TSP strategy was coupled with CV technology showed a lot better performance.
My name is Jahed. I'm doing my PhD in civil engineering, Dalhousie University in Halifax, and I'm finishing it soon. So I'll present today on development of a pedestrian microsimulation model accounting for social distancing strategy. And we did this work, we submitted a paper on these in TRB and waiting for the decisions. We are into a pandemic for a year. But we know that there have been other pandemics in human history before. But this one is novel and catastrophic. Around the world, during second wave time, the death toll went up to 100,000, and that number has increased obviously by this time. Coronavirus pandemic has brought significant changes in almost all sectors, including transportation system and supply chain management. Particularly, it impacts travel behavior and traffic movement in the network. Among many strategies that governments around the world have taken, non-clinical strategies, namely stay home and social distancing strategy, have been found most effective to reduce the spread of the virus significantly, particularly in Canada. Businesses and facilities are also trying to cope up with these complex newer situations to keep their customer safe from infection. But they need best practice information there to tackle these challenges. Particularly, international airports are of concern because they are a significant contributors to the spread of the virus. We have to keep in mind that there is already a shift in pedestrian behavior from a business as usual condition to pandemic conditions. So, airport authority should be, or probably they are being proactive in implementing strategies to keep pedestrians safe from infection. But we need to evaluate and test those strategies before commencing to assess the impacts on airport activity and operations. And that's why my study got motivation and that led to developing a pedestrian microsimulation model that accounts for social distancing strategy. So my study develops a pedestrian microsimulation model that will account for social distancing strategy for an international airport in Ottawa. I use PTB VSIM 11 and its add-on VisuWalk to develop the model, and I utilize different commands within the VisuWalk to develop the model. For example, you can use area command in the VisuWalk to define the floor space, and there are other commands like obstacles to replicate the kiosk and other places where where pedestrian cannot move. So those kind of obstacle you can define within the model. And there is a direct command for escalator and stair to include that within the simulation model. We choose the Ottawa International Airport third floor because that floor is directly connected to ground transportation, and there is high traffic activity on this floor due to arrival and departure activity. To facilitate pedestrian movement within the simulation model, I use partial routing and static routing. Partial routing facilitates stopping like in an intermediate places of a pair of origin and destinations. For example, you'll wait in a spot like in front of the service counter for the service in the airport. So you need to use a partial routing to make a pedestrian wait in that area. And static routing basically define the origin and destination. So to model the queue of the pedestrian in front of the kiosk or service center, service counter, you need queue modeling, which is already included within the visual, and all these components like the partial routing, static routing, waiting area, queue modeling. These components facilitate social force model to replicate pedestrian movement within the simulation model. You can see the pictures from my model where you can see different types of routings and origin destination locations, stairs and escalators. So social force model has several parameters to replicate the pedestrian movement, like the XY directions, on also the relaxation time, inertia. So and the responses to different events. So you can model all those pedestrian behavior using the parameters of the social force model. I'm not going through all the parameters one by one, but I can discuss the parameters in detail in later time. Please feel free to contact me. But I will mention two parameters though here, which are at the right bottom corner. You can see a socio-isotropic and de-socio-isotropic. These two parameters govern the forces among pedestrians based on the distance between pedestrians. The distance I'm talking about here, that is basically body surface to body surface. And you can see the equation of the force, that is repulsive force equation, and this equation is a vector because pedestrian movement is directional. So you can see a small unit vector at the end of the equation. Now, the most challenging part is the calibration of the simulation model. As we will be using this simulation model for social distancing scenario analysis, so we have to calibrate the parameter values of the social force model so that we can create a social distancing environment within the simulation model. I followed 3 steps to do the calibration: visual observation, sensitivity analysis, and parameter combinations. Based on my 7 years of simulation experience, I realized that visual observation is one of the important methods to identify error, and like, for example, coding error, unrealistic vehicle or pedestrian movement. So you have to really look at your simulation model to identify those errors at first glance. And then, so in the visual observation, you can identify different values of the parameters that may lead to unrealistic pedestrian movement. You can see in the pictures, people are circling each other, but that's not usual movement in front of a service counter, right? People have to be in a straight line queue like other places you can see in the picture. So you have to find out those values of the parameters that may lead unrealistic pedestrian behavior. And then once the parameter value that gives us the realistic pedestrian behavior, we can do sensitivity analysis using those values to see how different changes in the values of the parameters impact different performance criteria. For example, average speed of pedestrian, density of the pedestrian. And as we are talking about the social distancing, we need a lower value of the pedestrian so that people are apart at a higher distance to like at least greater than 2 meters. And then like the visual observation and the sensitivity analysis involves each parameter separately for analysis, but the parameter within the social force model will work together. So we also need to take a look at the parameter combinations and how it affects, how it impacts the pedestrian movement within the simulation model. Now, how to choose the right parameter values for the social distancing scenario analysis within the simulation model. So we know that the social distancing is basically keeping apart like these 2 meter or greater than 2 meter for the social distancing directives. Now the combinations of the parameter that will yield minimum number of pedestrian movement instances where pedestrian comes closer than 2 meter, we'll take that combination because we want less number of pedestrian contact closer than 2 meter. And that was the and that will be our target combination for scenario analysis. So this table basically showing all the social force model parameters, their descriptions, and the criteria I used to evaluate these parameters and their values. You can take a look at these. I'm not going in detail through this table, but for the results of the calibration, what I found. Three parameters, which are VD, A socio-iso, and B socio-iso. These three parameters within the social force model govern the distance, like the forces between pedestrians based on the distance between pedestrians. So as we are talking about social distancing, and distance is really a crucial factor for the social distancing. So these three parameters are the main influential factors to create a social distancing environment within the simulation model. And I also showed some results from the sensitivity analysis for these three parameters. You can see if we increase the values of these three parameters, pedestrian density decreases, and that's what we want, because in a lower density, people will be apart at a higher distance, at least 2 meter or greater than 2 meter. Now, after the visual observation and sensitivity analysis, we have now those values of the parameters that gives you the realistic pedestrian behavior. So keeping all other parameters a constant, like using all of the values, like constant value for other parameters, I only varied these three main parameters to create combinations of the parameter values, and I ended up with 29 combinations of the social force model parameters. I run each a simulation for each combination 3 times for each combination, so that gives us 87 simulation runs. And for the sensitivity and visual observation, I run 210 simulations to identify the right appropriate parameter values. So in total, around 227 simulation runs were conducted for this study. So when I run the simulation for each combination, what I found, there is a combination that gives us 3.8% of all instances that demonstrated distance among pedestrians of less than 2 meters. So that this combination yields the minimum number of pedestrian movement instances that gives you pedestrian contact less than 2 meters. So we choose these combination to run the social distancing scenario. Now, how we do measure the distances between pedestrians? So what I did, I stored XY coordinate of each pedestrian at half-a-minute interval from the simulation, and I run a Python code to find the distance from a pedestrian to all other pedestrians at half-a-minute interval, and identify the number of instances that gives you pedestrian contact closer than 2 meters. And combination 28, which is not shown in the table, that is our target combination that gives you the minimum number of pedestrian movements that demonstrate contact closer than 2 meters. So once we get our social distancing parameter values, we run the simulation for scenario analysis. There were 3 scenarios that I run. Scenario 1 was the pedestrian movements with no social distancing parameter in effect. I mean, we use the pedestrian parameter values from our earlier studies for a base case scenario. But for the scenario 2, we use these combinations to do the social distancing scenario analysis. Scenario 3 is also social distancing scenario, but in combination with service enhancement in the airport. The service enhancement means we, as social distancing strategies potentially like the delay the activity time in the airport and the travel time. So we try to see if we increase the staff in the service counter, does it improve the performance of airport operations? Let's take a look at the results of the scenario. So you can see here for the scenario 1, there were 10,312 instances of pedestrian movement that demonstrate pedestrian contact less than 2 meters. But when we apply the social distancing parameter values obtained by visual observation sensitivity analysis and parameter combination, that significantly decreased that the number of instances, and it is with respect to the base case, like scenario 1, it is 92% and 93% in scenario 2 and scenario 3. Now for the travel time analysis, we can see that scenario 1 has lower travel time, individual lower travel time part. For scenario 2, when social distancing directive is in effect, travel time increases due to the queue in the airport. But when we double the staff at the service counter, though there is social distancing directive in effect, travel time improves. And these are more origin destination travel time analysis for the Ottawa International Airport. When there is social distancing directive in effect, we can see that the similar kind of results here. Scenario 2 offers a higher travel time with respect to scenario 1 when there was no social distancing directive. But scenario 3 obviously gives us a better performance because there is social distancing directive in combination with the service enhancement, like the doubling the staff at the service counter. Now this results gives us some policy insights. Here we can see two pictures. The first picture refers to the scenario 2 when there is only social distancing directive in effect, and we can see a long queue outside the airport for services. People are waiting here to enter the airport, and as we are not allowing more people inside the airport due to the social distancing, people have to wait outside the airport. So a pedestrian can enter the airport only when there is an unoccupied service counter. Now this results indicates that we need infrastructure modification or new infrastructure development in the airport complex to accommodate this kind of QE due to social distancing strategy. But sometimes, but in Canada, what will happen if there is a winter? You cannot even wait outside the airport due to snow and other reasons. So we might have a virtual queuing system where you can put yourself in a queue online and you will arrive at the airport within a specified time interval. But anyway, we have to also prioritize those pedestrians in the virtual queue management who have an immediate flight or emergency flight. So those kind of strategy and infrastructure modification might be required by the airport authority to accommodate non-clinical strategy to prevent the spread of the virus, infectious virus. And yeah, so that was all for my presentations, and I would like to acknowledge COVID-19 Alliance Grant and Natural Sciences and Engineering Research Council of Canada for their support in this research. Thank you so much.